Well, in each talk we have 30 minutes time. Of course you can ask questions, but for very controversial questions which would take a very long time, we should wait until the lunch break, because we should respect the lunch break. Because I think we all...
Okay, thank you. So my talk today is essentially a continuation of what Nikolai was talking about, and I will focus on magnetic Doppler imaging, reconstruction of the structure of magnetic fields and stars. And since Nikolai has very nicely presented the techniques, I will more concentrate on the recent results. Well, I guess I don't have to explain you why we use magnetic Doppler imaging, and throughout this talk I will use a different acronym, ZDI, Zeeman Doppler imaging, just not to confuse the solar people who have reserved the MDI acronym for something else. So basically, the Zeeman Doppler imaging is the best method to interpret high-resolution spectropolarimetry of stars, and it is probably one of the highest, together with Doppler imaging, it's one of the highest resolution methods in astronomy, in modern astronomy. And unlike the common study of magnetic activity through a variety of proxy indicators, the Zeeman Doppler imaging offers us a chance to obtain direct access to the information about magnetic fields and study how surface magnetic fields in stars are related to surface structures like spots, chemical spots for hot stars, and temperature spots for cool stars, and also tell a lot about interaction between magnetic field and matter in a circumstellar environment. And there is a variety of things we can study using Zeeman Doppler imaging, such as magnetic field itself, long-term modulation of magnetic field structure. We can measure differential rotation using magnetic tracers, study magnetospheres of stars, and this list goes on. So recently, during last 10 years or so, there was really an explosion of Zeeman Doppler imaging studies, thanks to availability of high-quality polarization measurements, spectropolarimetry of stars. Until recently, until this explosion, we basically knew only about dipolar-like fields, strong kilogauss dipolar-like fields here for the so-called APBP stars, magnetic chemical peculiar stars. We also knew that some fraction of white dwarfs also possess these simple low-order multipolar fields. But recently we started to detect magnetic fields in really massive stars, those that become supernovae at the end. We discovered complex magnetic fields in AP stars, and we are now understand better what are really the structure and strength of magnetic fields in a variety of late-type active stars. So this is essentially the plan of my talk. I will work my way down the chart diagram presenting you results on magnetic Doppler imaging obtained by our group and other people, mostly, of course, the major player in this game is Jean-François Donati and people working with him. So, starting with early type stars, magnetic AP stars, these stars have rather strong magnetic fields, typically kilogauss and more, and these fields are believed to be fossil, meaning that stars have acquired somehow, we don't know how, but somehow they acquired these fields during their formation, and then the field remains stable on timescales accessible to us. And these fields are accompanied by chemical spots. And this simple animation shows you the inclined dipolar field, and as the star rotates, we see how stellar line profile recorded in all four Stokes parameters here, how it is changing. So this is intensity, this is circular polarization, and linear polarization, Stokes pure new parameters. For the, yes?
What is it I? What is it B? Better. What is alpha?
This is simply the parameters of the dipole that I assume here. I, it's an inclination, the angle between line of sight and the rotation axis of the star, and beta is the inclination of dipole with respect to the rotation axis.
Thank you.
So in the analysis of magnetic AP stars that we are doing mostly, we are modeling individual spectral line profiles using 4 few stars now, and this list is gradually expanding. We are able to interpret all 4 Stokes parameters as shown here, and we are also doing simultaneous reconstruction of chemical abundances and magnetic field. And this simultaneous thing is really important because we take into account the influence of magnetic fields on the reconstruction of star spots and vice versa. So there is no artifacts coming from inconsistent treatment of different surface effects. In situations when we have all Stokes parameters, it's possible to reconstruct magnetic field directly, just mapping each vector component of the field without imposing any a priori global model of the field. However, if only circular polarization is available, we need to constrain the inversions more strongly, and for the early type stars, what people usually do is assume that their fields is described by the low order multiple and then fit parameters of this multiple. This slide is supposed to give a very brief overview of current theoretical understanding of early type star magnetism. And basically what we now understand since just a couple of years, there is some critical field strength believed to be around 300 Gauss for the dipole field strength, above which the field is fossil field is stable and it can withstand shearing by differential rotation, and it should have a structure like presented here, and this is from studies by Jonathan Brestwaite, O'Connell, and collaborators. They basically find that the field is stable on long time scales if colloidal field is combined with this toroidal structure which hides inside the star. So this is how strong AP star field presumably looks like in 3D. However, for magnetic fields weaker than this limit, global magnetic field cannot survive shearing by differential rotation. So perhaps the structure of magnetic fields is more complicated, like shown here from the simulation of Rainer. Modern spectropolarimetry now reaches sensitivity where we can really detect very weak magnetic fields like those shown there. Starting from massive stars, presenting some recent results, one important observational program that we are involved now is the large observational program at Canada France Hawaii telescope, where we try to observe essentially all O and B stars looking for the magnetic field in these objects. And what we're trying to understand is these topics are listed here. It's the origin of the field, how much the fossil field is present there, and maybe there is also some dynamo effect, the role of magnetic field in stellar evolution. And what is especially interesting for those stars is that magnetic field controls the mass loss. So instead of spherically symmetric wind, the star has a rather complicated interaction between rotation and magnetic field, and as a result the star gets this disk which is oriented somewhere in between the equatorial rotational plane and magnetic field plane. And the presence of this disk leads to a variety of phenomena like variation of H alpha and brightness variation, and also many interesting phenomena in X-ray part of the spectrum. Some early result of this analysis of hot stars, of massive stars, is this mapping presented here, where only 2 Stokes parameters were used, I and V, and the magnetic field recovered is basically that. We are going now to slightly less massive stars using SOFIN at NOT. We have done several studies of magnetic fields in classical AP, the BP stars. And really the advantage of softened spectrograph is that we can have access to different lines of different chemical elements and reconstruct simultaneously magnetic field and many, sometimes 15 or 20 different chemical maps. And this is very useful for comparison with theoretical models that try to model how spots form in the presence of magnetic field. One of the most recent studies that is hopefully will be published soon is the study of cool AP star that also pulsates in higher atomic and radial mode. So this is the structure of the field recovered for this star, and again this result is based on the circular polarization. Well, if we use all four Stokes parameters, results actually change rather dramatically, as Nicola already mentioned. So this is example of a prototype AP star, alpha 2 convent. This is the map that we can get from two Stokes parameters, basically a dipole. And for the same star, the same data set, adding linear polarization, we get structure like this. So still the field is more or less dipole in the sense that there is one hemisphere dominated by positive polarity and other hemisphere negative polarity. But look at the field strength map. It is much more complicated than expected for dipole. And I should emphasize that these small scale spots, they are not an artifact of inversion. You can really trace these small scale features in the Stokes Q&U profiles. You see corresponding perturbations moving across spectral lines. So this is really has a direct connection to observation. So what we now know about AP stars is that their magnetic fields are probably somewhat more complicated on smaller scales than we thought before. And now coming to cooler stars, the overall approach, overall methodology of Zeeman Doppler imaging of cool stars, the basic idea is of course the same as for hot stars, but the practical implementation is very different, primarily because magnetic fields in these stars are much weaker. So instead of using individual spectral lines, one really has to add together thousands and thousands of lines, constructing some sort of mean average profile, also known as least squares decomposed profile and short LSD profile, which is then assumed to behave as a real spectral line. And this assumption is not that was proven. We don't really know if LSD profile behaves as a real spectral line. And in all studies, Zeeman Doppler imaging studies of cool stars, people use only circular polarization, and typically magnetic field and temperature are reconstructed non-simultaneously. And there is a simplified model for, people also use simplified model for local line profile. Sometimes it's Milne-Eddington model, or sometimes it's simply Gaussian and it's derivative for Stokes V. And this animation illustrates you the impact of magnetic spots with different orientation of the field on the Stokes V. And what you can notice that depending on the field orientation, Stokes V behaves differently. For instance, for azimuthal field, the signature changes sign in the center of the disk, and the amplitude is maximum when a spot reaches the limb. Whereas for radial field, the picture is quite different. So this is the azimuthal field, seen in here, and for radial field, of course, the signature has the same sign and reaches maximum when the spot is closest to the line of sight. And based on this correspondence between the features in Stokes V and the orientation of the field, Zeeman Doppler imaging of active stars becomes possible. However, one warning that everybody should keep in mind when interpreting ZDI results of active stars is this effect of separate reconstruction of magnetic field and temperature, and using some test results, numerical simulation, I here illustrate what is the consequence of that. So what you see here on top are true maps of magnetic field, and the field shown with the color. So red corresponds to magnetic field, whereas contours show temperature spots with a contrast of 1500 K. So there are 3 spots. In one case it's purely magnetic spot, second case it's purely temperature spot, and third case it's the combined temperature and magnetic spot. Presumably this is the most realistic situation that we should encounter in real stars. And the bottom panel shows reconstructed images, and for the usual Zeeman Doppler imaging where only Stokes V is mapped, you can see that it's possible to recover rather nicely radial field in purely magnetic spot, but for the spot where magnetic field coincides with temperature spot, reconstruction doesn't do very well. I mean, the flux is shifted to a different place in the star. Whereas if one does it simultaneously in Stokes I and Stokes V, one can actually recognize that this is a full spot that has a magnetic field. However, the magnetic field here is somewhat weaker than was used for generation of simulated observations, and this can be cured if we, for instance, use simultaneously lines in the optical spectral range in the infrared, and the infrared has an advantage that there the contrast between spot and photosphere is smaller, so this magnetic signature of the spot is more prominent, or basically the same results can be achieved if we do molecular lines and inversions.
Infrared observation from satellites?
No, I mean it's rather near infrared, so region, for instance, around 1.5 or 2.2 microns.
Almost optic.
Well, for us it's infrared. Sorry.
It depends.
Coming to the results obtained for late stars, one of the early surprises, I would say, for structure of magnetic fields in active, rapidly rotating stars is the discovery of these strange structures in the azimuthal field. So this is the polar projection, and this is the pole of the star. This thick line is equator, and what you see here for the well-known RS-Civilian star HR 1099 is that magnetic field in azimuthal component is organized in this broken ring encircling the pole. And for a long time this was kind of debated very much, and many people didn't believe these results. However, azimuthal signature of azimuthal field in the Stokes V profiles is really very, very different from that of radial. So it's kind of difficult to get this result by making mistakes or as an artifact. And in fact, this year there was a simulation by Brown et al. That have demonstrated that if one takes a sun-like star and assumes that it rotates, say, 3 or 5 times faster, then the natural consequence of interaction between differential rotation and convection is the generation of these coherent toroidal structures on the bottom of the convection zone, which look kind of similar to what people get in the Doppler imaging. So this is something quite unexpected. Slightly increasing rotation rate for the star does not create more sun-like spots, magnetic spots. Instead, we get these coherent azimuthal rings of different polarities in the northern and southern hemispheres. And also these structures oscillate cyclically, they change signs, and this has also been observed using ZDI methods for active stars.
Change signs means they are able to compute 200 rotations?
Yeah, they compute like thousands of rotations. This is an elastic spherical harmonic method.
Yeah, nevertheless, it's a big step.
But I don't think that they saw any systematic oscillation of the large scale field. They did see sign changes.
They did or they didn't? They did or they didn't?
They did see sign changes, but I can't remember if they had a really constant period.
Well, cycle.
And what's the period of something shorter than
No,
50
it was
years?
quite a long period.
A long period.
Yeah.
So what was the statement to the, on the right hand side? Did it is the azimuthal field is coherent or it is uncoherent in fact?
Well, azimuthal field is as you see it in the picture. Do you say it's coherent or not? I don't know. I mean, this is observational result, and then it's up to theoreticians to interpret it.
Yeah, I wouldn't say that a simulation leading to a coherent field does predict or does confirm the observation.
Well, they're kind of similar, and of course, those simulations correspond to a region slightly below photosphere. Yeah? So it's not purely, it's not directly comparable to this. You can imagine that this can be a complete ring, but it is slightly below photosphere here.
I mean, normally the wind of a star would be dragging out the field to make any toroidal field radial, one would think.
I don't think they do.
The wind would change the field simply to make it radial rather than toroidal, even if it was trying to be toroidal on the surface. So is there any, like in the sun, you have the field which, as you see, the corona is going radially. Is there a reason that maybe there's no wind here in this thing, in this star? That this argument doesn't apply?
I think that there is a wind. Yeah, that's an interesting aspect, because these ZDI maps are of course used heavily for prediction of magnetosphere of the stars in comparison with X-ray observations, with prominence observation and so on. But people, when they do that, people only take radial component. They forget entirely about this evidence. Okay, so of course this is an interesting result that requires kind of confirmation, and what we are trying to do now, this is very much work in progress, is to introduce the more detailed methods of spectrum synthesis, polarized spectrum synthesis, into the interpretation of observations of polarization of lake-type stars. In particular, this is the work we are doing with Sophian observations of Ia Pegasa, and this is the map of temperature, magnetic field, and these two things reconstructed self-consistently using polarized radiative transfer. And we'll see what comes out of it. Maybe results will be very different from what was done before. Then going a little bit down in the HR diagram, spectropolarimetry now is so much sensitive to the magnetic fields in stars that it is apparently possible even to map, well, in a very crude way, but still construct some maps of the magnetic fields in solar twins. That is, stars which are very close in the parameters to the sun, like temperature within 50K and G within 1.1 X and similar metallicity. This is, for instance, the radial and azimuthal field reconstructed for a well-known solar twin 18 scope. And the scale here is just plus minus 5 Gauss. And what was demonstrated in a recent paper where 4 such stars were studied is that there is apparently very prominent dependence of the field structure on the rotation rate of solar type stars. If we look at stars rotating at around 10 days, they tend to have stronger field, so this green line corresponds to mean magnetic field strength, and the field energy is concentrated in the toroidal component. So this red line is the ratio, is the fraction of toroidal field energy. But as we go to longer and longer rotation periods, field strength decreases, and the fraction of energy stored in the colloidal component increases. So the message is, even for the star with the mass and temperature very similar to the Sun, things depend a lot on its rotation period, which is kind of natural, but still it shows how narrow is the region in the chart diagram where a solar paradigm works.
How people do these diagrams in the solar case? It's something opposite, I think.
Well, for solar case, we, in order to put the Sun on this diagram, we need observations of the Sun that fully mimic our observations of other stars. Observations of Sun as a star.
Colloidal field.
And for Sun-like stars, there are now also claims of observations of magnetic cycles, and these claims look like this. So people, for instance, reconstructed magnetic field on Tau Gu, the well-known exoplanet whole star, and these are the maps of radial magnetic field for different years. And they say, well, kind of the dominant field topology changes with time, and this is possibly an indication of the site. I don't know how to interpret that, but this is the claim. Cycles have been observed on solar stars.
1 year. 1 year cycle.
Yeah. Going to young stars, spectropolarimetry now is capable also to giving us some observations of rather faint T-Tauri stars, in which magnetic field is important because it's guiding the accreting material on the surface of the star, as illustrated here in the simulation. This simulations like that are now directly comparable to reconstruction of the global magnetic fields in the stars, like illustrated here. And then finishing with the really the bottom of the main sequence, rather interesting and unexpected results were obtained recently for low mass stars, M-dwarfs, and even brown dwarfs. Well, we knew for some years that these stars have very strong local fields. This evidence comes, for instance, from Zeeman splitting and broadening of spectral lines, like observations here in what we call infrared. And this is observations we've done with TRIRIS instrument of the Very Large Telescope, the TISO Very Large Telescope. What is shown here is the spectra of two active stars, active M-dwarfs, bracketed by inactive stars with similar spectral types. And these are lines at 2.2 microns. And you can clearly see that there is a splitting of these lines corresponding to kilogauss fields. We knew about these kilogauss fields, but what was also discovered essentially simultaneously in the simulations and in the observations is that M-dwarfs also possess a quite strong global field of mostly colloidal structure. So this is result of ZDI study, and this is result of image dissimulation. And this colloidal field is stable on many months, on the time scale of many months. So I would say that now there are three different types of magnetic fields on the HR diagram. The fossil global fields of AP stars, the complex toroidal fields of M-dwarfs, of solar type stars, and for M-dwarfs there is another change in the structure of the field, going from small-scale toroidal structures to colloidal fields again. And this is kind of summarized here in this complicated diagram taken from a upcoming review by Martin van Street. And basically this shows here the structure and strength of the field as a function of stellar mass and rotation period. The toroidal fields are shown with green and blue symbols, colloidal fields with red symbols. The shape corresponds to the symmetry of colloidal component and the size corresponds to field strength, going from 3 Gauss here to 1.5 kilogauss here. So as you see, the fully convective limit is somewhere here. So for end-wolves, fully convective end-wolves, field becomes really strong and it acquires a dominant colloidal component. There was also a suggestion that for these stars, the fields are produced by some kind of universal convective dynamo mechanism, which is also common for brown dwarfs and for planets. So by looking at these low mass stars, we probe action of dynamo, which is also relevant for planetary magnetism. And these are my conclusions. Basically, these are, I'm summarizing here what I already said. And I guess the main message that I have for you today is that solar paradigm of magnetism concentrated in small spots with mostly radial field is really, really limited in the HR diagram. And if we want to understand how magnetism of other stars operate, we have to get more observational results and not only extrapolate the solar models to other stars. So thank you.
In the last plot that you showed, that one, first of all, plotting dimensional quantities can be easily suspect because you're mixing large and small stars. It's much better to have a non-dimensional quantity, like for example, normalize it with the expected turnover time or some empirical turnover time. And then one wonders whether there's, if you plot this again in some other sense, like B versus B minus V, replacing mass by B minus V, which is often done, do you see then a correlation that matches those obtained previously?
Well, this is purely observational diagram. Actually, I believe the Rossby numbers are indicated by the dashed line, so there is some information that you wanted. But there is definitely a correlation between mass and B minus V. So
Yeah, that's almost the same thing.
I don't see how plotting versus B minus V.
No, but such diagrams have been done previously, and so one does not normally, as in the past, not so much project versus mass, but versus B minus V.
I think really the point of this diagram was to show transition to colloidal fields at the limit of the convective star, which is related to certain stellar mass rather than B minus V. The diagram is showing this.
And the size of these symbols gives something about field strength?
Yeah,
right.
it is proportional to
Yeah.
this.
And again, you can maybe calculate the, I mean, calcium HK is not available for these, right? Because they don't exist, is that right?
For some of these stars, there are no observations of cycles.
They were even proxies, other proxies. I mean, again, one would like to plot the field strengths in a non-dimensional way. And what is often done, of course, is RHK, which I think cannot be always done, of course.
Yeah, which is a proxy.
But it's something like B over B equipartition, in some sense.
Yes.
So one should try and, again, calculate such a dimensionless quantity.
So I guess if we talk about equipartition limit, fields here are approximately equipartition.
Here's our last question.
Imagine, like in AP stars, an oblique rotator. That means a dipole, this is a boloidal field, lies in the equatorial plane. Would you observe it as a toroidal field which is non-axis-emitted?
No. Well, you see, this is a result obtained by the same group that claims toroidal fields in the photostars. For low mass stars, they obtain colloidal fields. So it is rather easy to distinguish the two. I mean, the signature of such axisymmetric colloidal field would be a stable, more or less stable Stokes V signature that is not changing with rotation phase, whereas for azimuthal field the signature will be.
Maybe it's like a square dynamo.
That's the background of my question.
I think we continue. Let's thank Oleg again.
So I am Jan Pitt from Turtle Observatory. This is not very far from this place. And this is on nose. Look at him carefully. First, there is a paper on the table, and this is a printout from the computer. And what is depicted on this paper is surface on the sun, something like that, 5,000 kilometers by 5,000 kilometers. And in his hand, it has a model for the star. He wanted to model spherical convection in a star. And it was very, in the very early times, he was forced to use computer Minsk 32. We had a memory of 16K, and then it did 30,000 flops per second. Still, he was able to model the surface of the sun with aid of the compressible, radiation-coupled, non-magnetic, gravitationally stratified medium. And he got indeed something running there, very nice, and got a lot of results. And this was a nice period in the time of the solar research. But then he introduced me to the ILCA. I think it was somewhere in the late 80s, 86 or 7. ILCA proposed to me to do something with the sun. And the reaction of mine was very simple one. No, with sun there is nothing interesting going on, because the time series about sun, this is the most standard time series at all in the literature of the mathematical statistics. If you open the book about mathematical statistics of time series, the first time series you always see is this one. And I don't think it has nothing to do with that. There is everything is what is said is already said. Then he started to go around. He said maybe this and that. So at the end we agreed to do some things, and this is just fast overview what we did and what we do even now with this very standard time series. The first thing we looked at was with Pentti. Effectively, Pentti was the leading man in this group in this time, and we looked for the time dependence of latitudes and all the sun northern change in latitudes and southern change of sunspot distribution in latitudes, how it depends on time, and we find a very nice correlation, what you see, very strong correlation indeed, and we saw that there is a certain period, I think it was some 90 years, and it's so-called Gleisbeck cycle. It was known before, but we showed it in very strict and nice term on this plot. It was our first collaboration, which was devoted to the sun. And then the next paper in this series was a strange one. The bad thing is that nobody saw this paper, I think. It was published very openly, but probably it was too strange to look at. What we did in this paper was we took these butterfly diagrams, which you very well know, and we slightly distorted them in this sense that we wanted to put them look more. Let us skip this one. Okay. We wanted to see it in more standard statistical way. You see, the problem with statistics nowadays is this one, that if you use a very standard techniques, then you must introduce the Gauss distribution or something very similar to that, very, very simple things. But as you see, the distribution of the butterflies is not that nice at all, and you cannot describe it by the Gaussian or whatever. So that what we looked for was something more statistically normal. And for that purpose, we turned the wings of the butterfly so that in the results we get more or less normally distributed stuff. The nice point about this modification was that we got first the Gleisberg cycle once more again, but this was not important. But important thing was that we got these diagrams. So what they mean? You see, if now we have these butterflies, then they have these places in between which are more or less not covered by the spots. And after we transformed them, we were able to statistically characterize these empty places in very simple way. We just computed so-called quantiles, and we looked for the certain quantiles of these very nice distributions and computed difference of them. So in this way we effectively computed the fits of the these I mean, let me see again. What we effectively did, we computed the width of these spotless parts of the distributions. And we saw a very nice regression here. Now this is depending only which kind of quantity we took. And you see, it started from the high Deaver numbers of solar cycles. This was the last cycle we took into account because it was old work. But the important thing is that we predicted there in this paper that it is not possible to go further in this way, because then there will be no time to revert the magnetic field. They started to be already so tight. And this is what you saw now. That is what we saw now. Something was wrong with sun, and we were able to see it already, I think it's 10 years ago, before that cycle. But now it's not coming and not coming, and the other one is not ending and not ending. So this was one of the papers we worked on together. Now, the other topic which is interesting and which is connected to the sun is connected to the so-called flip-flop effect. And as Ilkas told once, that he remembers that I gave his name the flip-flop, but I am not very proud of that because it's very controversial stuff indeed. This is connected to the non-axisymmetric stuff of your dynamos, which I don't understand at all. But for me, this flip-flop stuff started from other spotted star of 8K Coma, and Lauri Ertsul, now director of the Helsinki University, worked on this star, and he was not able to fit one single periodicity into this light curve of the star. And then we played around with this data, and at the end of the day, I come to that if you do not want to put all points into one curve, you can divide them into two. And then you will have this kind of picture which is sometimes we call them glasses, but in this particular case it's not plotted as glasses, but you can plot it in shape by the half of the faces. And we got these glasses. The important point here is that the data which is put on this diagram is of particular kind of. That means that it was so-called normalized data. That means that if the amplitude of the star went down, then it was slightly magnified, normalized. And if it was too high, then it was squeezed. So that essentially these are the normalized magnitudes, and this allowed us to compute very precisely the period for this star. So that we didn't use the full diagram, we just divided into two and then looked for the best fit to these glasses. But this, and now these are now minima and maxima of this variability, and you see they are occurring two corridors, and these corridors we use just to compute exactly the value of the periods. And now people started to think, okay, that's very strange, very nice, that it occurs that the star is bright on one side, time to time, and then it switches over to the other one, and makes these flip-flops, so that strong axisymmetric component in the brightness on the surface may. Why I am unhappy with this? Because in principle it can be, probably it is, even as far as this FK comma goes. But now we do with mathematics. You see the formula, very, very nice formula. The problem is that people very often do not recognize, don't know the very simple thing that even if you have very continuous variables and you do with them very simple mathematics, you can get discontinuous answers or chunks. And just to demonstrate, very simple one. If you have 100% strong modulation of the harmonic curve, then in the moment when the modulating frequency, modulating phase goes from plus to minus, then phases of all the other parts of the curve change abruptly. So that effectively you have here only two very simple multiplied waveforms, and as you see on this plot, it goes in this way. This is a modulating curve, and this is the carrier frequency. And you see if the modulating curve changes its seams, then phases to the 180 degrees jump. So the flip-flop effect, I call it natural flip-flop effect, takes place in every modulated, at least 100% modulated curve. And this must make people careful with the flip-flop stuff. In the text of the spots, it looks like this, that if you have two spots, and if they rotate with different speeds, then it's not ruled out that this pattern just can come out from this differential rotation, but not from the, but you have the alternative is this flip-flop or whatever. Okay, this I told you. These are two frequencies, and now this is just minimum and maximum to see. It's very easy to get flip-flops from this plot. It was very simple wave effect, modulated wave. So now, if you have indeed a problem and you want to find out D-star flip-flop on the star, I mean now, not the natural flip-flop, but the flip-flop in the sense of true non-axis symmetry, then probably you must look for this surface imaging of this kind or other kind. But I am afraid that even in this context you can be fooled by the same mechanism, because you integrate by taking only very low frequency modes, and still these intermodulations can show up as flip-flops, even if you see them as probably on this plot. I do not know how to interpret these plots. These are done by the Svetlana Berdyukina. Unhappily, she is not here. But in principle, you can, and these are not these normal reversion. These are kind of very advanced science, which I cannot get. But in principle, I must warn you. You must be careful with the non-axis symmetric stuff. Now, with this flip-flop business, people started to work with these railways. And the railways are just plots which you will get when you plot the minima and maxima. And then you put these railways through these plots, and if you are happy enough, you can get the places where minima goes in the correlated way, or maximum goes in correlated ways. And as a result, you can claim that you can see flip-flop stuff. This can happen also if you work with the spots on the sun. And this was done by Berdyukina and Usoskin, and they got these kind of nice railways, and they effectively plotted the minima and maxima and moved in the phase to get the more or less coherent railway pattern. And after that, they found that there is even the flip-flop there going on, and this paper then was criticized by us. What we did effectively was these are the results. Long story to go. I only know 5 minutes to go if you want to go on time to the lunch. We effectively did a statistical Monte Carlo analysis of the method to find the flip-flop stuff and railway stuff on the sun, and we were able to show that even if you take a starting point random distribution, you still, if you use this methodology, you can get the railways out of that, and even the flip-flops. Okay, of course they were not very happy with this result. This is now our Monte Carlo stuff, you see, very nice. Two railways, very, very clearly seen. You can look at this paper. And then they worked out the other method to prove that there are indeed railways, and now they got even much more better result. The railways which are striped and they run in coherent way 120 years. So that means the sun must have inside a certain kind of, we call it phase, and now the phase rotates and rotates, and very, very coherently so, full 120 years. Of course, after that, of course, we were not very happy with this, and started to look at this. We tried very carefully, step by step, to repeat the result, to get the same result, to check it effectively. We were not able to do that, and it occurred that something is terribly wrong with this paper. I will show, maybe, let me see this picture. It is single space to show what kind of problems we have. You see, this is a lot of certain, let us call a statistical indicator. which measures statistical probability of certain parameters. This is 14.3. This is turns degrees per day for solar rotation, and this is the speed. How this depends on the latitude. Yeah? And this is kind of parameter which measures how good fit you get for this differential rotation model. Because to get coherent picture for the railways, they used corrections. They used corrections to the longitudes with certain parameter, and now they optimized for this parameter and for this parameter. Now they got this kind of distribution here, as I saw. We repeated the computation and we got this kind of distribution. This is absolutely different. And you see, they are slightly strongly correlated and so on. That probably the latest one is true, can be seen simply from this formula. You see, this is now that these corrections which go up. This is positive term here, and this is positive term here. Because they are all positive, you sum up the curves values here, they cumulate. That means that effectively this one is rising curve. I will show you on picture, and this one is just line going up recursively. And now that means that you can always compensate the rise in this branch by the decline on this branch. And that is just what you see on this picture. Okay, so that something was wrong with this paper, and I must stress that probably you do not need to believe. Why I tell you? Because I consider this important. I consider this important because this is not just one paper what was probably wrong one. There is a certain kind of our intuitions which spoils the analysis, because we are not ready. It's harder to switch over if you think in the terms of linear stable and in the terms of rotation. And this makes people sometimes very unwary that the rotation itself brings in a certain kind of statistical correlations which came from the other side of the circle. So that this is, I think, a good example of this, but I do not have time to go into very deeply into this. And the last point, but I want to make because time is over, is that the conference is devoted to the ILCA, and ILCA is working still now. And this is just work in the progress, what we are doing now. We try to look for, assume that on the sun there are railways, but the railways are shorter. So how long are these railways? How long are effectively the correlations in the non-symmetric components of the field? And for that purpose, we do a very, very simple thing. We wanted first to ignore every statistics what we knew before and start from the very simple, absolutely non-parametric point of view. And I tried to show it with my hand. You see, if you have a certain distribution of longitudes on the circle, yeah, this one. And now you have the other one, this one. And they are different. Then you can compare two distributions in this way, that you look for every longitude on this circle to the nearest one on the other one. And now you can go further, either looking how far this nearest one went through the jump, or the longest jump altogether. That means this is the most innovating new feature on the sun. this kind of statistics, and based on these metrics, you can build up mathematical statistics now of the full strength, where you can analyze correlations and also the mean movements. What we do now, if you want to analyze, for instance, rotations, we just make these longitude correlations, then we have full lot of these circles time dependently, and we look for the this kind of movement or rotation which best fits to certain rotation speed. And as a result, we can get this kind of curve. It's extremely nice. It shows 14.34, something like that. And it shows the mean solar rotation, but and now comes the important point. This plot is computed not by using solar spots in this sense that you have one spot and look how fast it goes around. No. What we took effectively was sunspot groups. We started from the sunspot groups. Then from all the sunspot groups, we took only one and the first observation of them. You see, only one when we first saw it. And then we started to look effectively not for the sunspot groups, but the longitude groups, or effectively this is even not the longitude groups. But, let us call it active region, but because I think you have this active region as a term in your theory, but we do it in the statistical sense. Effectively, where activity is, and we assume that if the group started from here, and the next one, which is not connected to this one, is now seated here, then this structure of the jumps from the nearest one, if you change these parameters of the rotation, then you can look for the best fitting rotation speed or correlation speed, whatever, using only metric which is between the sunspot groups, in this sense that you compare only the places where they started when they were first observed. It's very important because most of the solar rotation work is done in the terms either by the sunspot moving, by tracking of the sunspot, either by the tracking of the Doppler images, or I think some people work with this helioseismology, or they take it in their own way, always, as always. But we work just formally started from the very little numerical tables where we have only sunspot group observation and the starting point. Okay, and the last word is this one. I must skip this, of course, where we get the differential rotation of that. You see, we do not track the spots. We do not track the spots. We only look for this background and bulk movements by this statistical method. And at the end of the day, we can get this kind of correlation curve when you can see that if there are some correlations, and if these active regions exist, then not very long time, maybe from here to here, that's up to you. It's very hard to tell now where you will get the asymptotic level. But we say something around 15 solar rotations. So that is the work what Ilkka is now doing. I mean, I am computing and he must comment. Hopefully. So, thank you.
Some quick questions?
I didn't believe in Uslovsky-Berdugina result until a few years ago, because this the whole idea about active longitudes, based on statistics, maybe not appropriate, because active longitudes are best observed when activity is not high. So when activity is low, then it's very clear that most active regions appear at some preferred longitudes, the volume of activity. And years ago it was amazing that you can see the active longitudes 180 degrees apart, and activity appears on one side, on another side. I didn't do statistics, but I just saw it in the data without statistics, particularly at the end of this solar cycle. So maybe it's all statistical analysis. It's very difficult because at solar maximum, when you have more sunspots, everything is mixed. So then you actually don't see active longitudes and you don't see cliff slopes or something. But maybe there is still something that was happening like this, because if you look at some periods when active longitudes are prominent.
No, I mean that there are certain correlations, and I think that these correlations take some up to 15 cycles or so, of course. And the strange point is that there is so exact numbers in it, in this sense that there are this underlying structure rotates very nicely. It has a very strict parameters. So
well, because it's rotation.
Rotation. Exactly.
Latitude, everything is mixed, so you don't see.
And you can see it even not to looking at the sunspots themselves, but just from the places where they occur. So that are effectively, this must give information from somewhere deeper. I think that is true.
In years, how long is your track, railway track? No, you didn't answer this.
Full data set from 1875 up to the now.
Yeah, but I mean, how long? For how many years is there?
15. Up to the 15 solar rotation. So up to the 15. That means
that's quite long.
15 periods on rotations, 15 months.
Yeah, not bad.
Yeah, no, you see, but I'm not 100% sure. Here is asymptotic level. Now you can see. You can decide yourself.
Yeah.
That's the point. The statistic itself is so simple that it does not give a very strict limit.
Okay, let's thank Jan again. The next speaker is Rainer Alt from Potsdam.
All right, I'm talking about observations of the sun, but not very recent and not very precise ones, but still very interesting ones. The question is, the title is extending the solar butterfly diagram into the past, and the question is, can we go, we have heard about all the observations from the Greenwich time and up to now, and the question is, can we extend this solar butterfly diagram into the past? The answer is yes. Hitler was actually doing work on this by analyzing the Spörer observations taken from Potsdam, but he didn't find everything in Potsdam because there is more. And that is the observations by Johann Staudacher, which I found in our library in the archive, and these cover about 50 years, precisely 50 years in the 18th century. And these are all drawings of the sun. You can see a typical example of them. And the question is, can one do anything with them? It's covering about 1,000 days. Positional information is available for actually 999 days, which is not a joke, it's accidentally like this. Some of the days are combined into one graph, so that's why it's fewer drawings, but more days for which we have information. Can we learn something about this guy? There is actually nothing known except when he was baptized. Otherwise, we don't know anything about him. We also don't know what kind of telescope he was using. So I had to look through all these information he has drawn there. Why is it wiggling so strange?
Well, probably it's the VGA number, which is I think.
Okay. That is okay. Does it help if we resynchronize the projector somehow? Is this on? Maybe you can do one. There is only one single information about his telescope in an observation where the Saturn was occulted by the moon, and he was talking about a 3-foot sky tube. And so that tells us it must be have 3-foot length, and this would be, by the Nuremberg foot at the time, would be 91 centimeter, typical telescope of the time, probably with very small aperture. If you look further, you see that there's almost no indication of a penumbra. Here is something like a penumbra, but this is very, very rare occasions when you can see it. Usually he hasn't seen it, or at least he hasn't drawn it. Well, it doesn't stop wiggling, but maybe it's not so bad.
We can get the penumbra eventually by pressing the button.
Excuse me?
We can get the penumbra by pressing more of the button.
Maybe. Right. So, and if you go back in time and see what other people have seen, like the famous Alexander Wilson, who observed the Wilson depression near the solar limb, he has very precisely drawn the penumbra of the sun. Even if you go very, very much back into the 17th century, one of the first drawings, even there the penumbra is sort of indicated in their drawings. So we may conclude that Staudacher was using a very, very basic telescope, but still we have the positions of the sunspots and we can probably use them for something. The question is, of course, there is no solar equator, no ecliptics, no horizontal system, nothing. How can we find the orientation of the solar disk? There are some very nice things. There are solar eclipses drawn into the book, from which we can find out, if you overplot the ephemeris of the solar eclipses of these events, then you can find out that all the images he drew were mirrored. So he was using the projection method behind the telescope, and we can just mirror all the images. Question is, what's the orientation? And you can see actually two examples, and here both orientations, like upside down and correct and upright orientation, were used. Perhaps he has even changed the telescope from a Keplerian to a Gregorian, which would rotate the image. We don't know. Also, the accuracy of the spots increased at some point, so this may indicate that he changed the telescope halfway through his life. Now, first you could think, oh, nice, there are some lines drawn in. Sometimes they're even annotated by an E or EK. German word for ecliptic would be with K. And you could think of, oh, that's great, we can just use these lines and get the orientation of the disks. But as you see in this example, this is probably not true. If you see the typical distribution of the spots here and the ecliptic going vertically through them, that really can't work. And also, if you see the writings of these annotations, they are not in the writing of Staudacher. And it became quite clear to me, meanwhile, that these were added later by somebody who also tried to analyze the spots. And this guy was nobody less than Spörer himself, because Spörer got the book in the 1980s somehow. Also, then it was catalogized in the library in our institute. And he tried that, and he drew in these pencil lines. But I did not dare to use them because they appear to be not very representative. So what I was doing actually, was using in most cases the rotation of the sun by taking disks of adjacent days, or days which are not too far apart, here it's 4 days, and you can associate spots on different days moving across the solar disk. And you rotate both disks against each other until you find the optimum orientation of both disks. And this is what is done here. So I overplotted these. And you see the other one, which is a bit grayer here, is a bit rotated against the other. And then this is one of still of the period when you drew upside down, so north is at the bottom. And that's why it's rotating like this. You see, turn it around. Right, this worked quite well. There are also extreme cases when you have just a single spot observed on 2 days. And you could say, oh, fine, then this is the equator. But of course it's not, because both drawings were made on 2 days with 2 different rotations. So again, you have to rotate both disks until you find the optimum distance according of the rotation law we know today to say what was the equator. If you have 2 spots, you get 2 solutions. In that case, I took the most likely one. So if one of the solutions produced spots near the pole or so, I just rejected that. So that was subjectively then done. You can actually see that there are some notes about days when he didn't see anything. This means nichts, nothing, on the 2nd of April. So these are additional information which don't help the spots, but they're, of course, they were used for the sunspot numbers. Then you can even go more extreme if you really if you don't have anything like adjacent observations or something like this. You could even use the bipolar groups, assuming this is a bipolar group, and still allow for a certain tilt, which is on average 4 degrees, but this of course has a very, very large scatter, and assume that the solar equator was more or less parallel to this bipolar group. Again, we are still in the set of upside-down images. So this is a crude approximation, but we are talking about statistical analysis here, and not so much about the precise individual spot, the very spot here. Or you could just go for the distribution of the spots. That was the image. I think we have noticed another one. So where you could say, well, this is all very likely indicating the equator. So you draw something like this and assume this is the coordinate system of the sun, the most likely one, without any rotational information. So these are the essential methods which I used to get the sunspot positions. There is a lucky case where you drew the sun twice on the same day, and you can see what the accuracy is roughly. So you see a few spots which are moved always by a couple of degrees. This is about the accuracy you can expect from these observations. So maybe 3 degrees. Most of the error comes, of course, in from the observations where I couldn't fix the rotation very well. Then this is the largest error. And then there were even more observations. When I showed this in Armagh recently in a talk, I asked, well, do you have by accident, because that observatory was founded in 1790 something, do you have by accident some solar observations? And they said, yes, we do. There were actually micrometer measurements. They tested their passage instrument and were doing micrometer measurements. So the only information you have is numbers and passage times. And from the combination of all these numbers, you can reconstruct the position of the spots. In some cases. It was very few spots, but since the end of the 18th century is extremely interesting, because there are very few observations, also these were taken into account. There is a period when Staudacher didn't observe much, that is in the 1750s, and this is nicely covered by observations by Ludovico Zucconi from Venice. These have now also been measured and analyzed by José Vaquero and his colleagues. So I will include these in my results I show later on. There are even more observations. This must be a very large set of observations, but I don't think it is still available. It is to some degree probably destroyed or lost. I don't know. Some of the data were analyzed by Spörer, but only a very small set. There is these observations in Danzig now in Poland, and these were actually already measured. I just had to find out what sort of coordinate system he was using, and then I can include these data also in the 18th century butterfly diagram. But the interesting time is still very poorly covered. Only verbal reports, no proceedings. Descriptions of something. There was a nice group near the limb of the solar disk or so, but then you don't know the latitude, and it doesn't really help. There's no way of finding out something useful. So, that's what it is. That's the butterfly diagram in the 18th century. Now we have almost 5 cycles here. And I've added here in a bit darker color the positions by Ludovico Zucconi. They actually fit nicely with the positions by Staudacher, so Staudacher wasn't doing complete nonsense. And the very interesting thing is, while here everything looks like normal, you have a butterfly diagram, the butterfly diagram here, it doesn't look terribly normal, but you could say, okay, this is still a butterfly, but this isn't really a butterfly. This is like having a maximum in the middle, maximum latitudes in the middle, and many, many spots on the equator, and the same is indicated here, although the coverage of the cycle is a bit poor. So there was something wrong with the butterfly diagram in that time. Remember also that we are not too far away from the Maunder minimum, which was somewhere here, when spots were mostly on the southern hemisphere. So perhaps the cycle didn't get into normal after the Maunder minimum. This could be one explanation. Or it is really some additional mode, like a quadrupole mode or so, superimposed with the dipole. Here's a magnification of the Staulacher positions only and the Zucconi positions added here. I've added here also green bars where there were no observations for more than 80 days to show you where the real gaps are. So some gaps are real, some gaps are just no spots were seen. And you see this very nicely fits into this picture actually. And I think the accuracy of the Staulacher data is sufficient to make the conclusion that the butterfly diagram was not butterfly-like at the time. Right. And then I added a few more, so we have now seen all this to the left from here. And you can also try to fill up the 19th century up to the Greenwich data. And here are a couple of positions I found in the literature, mostly analyzed by Spörer. But they're not really enough to say much about the butterfly diagram. You can see here the nice wings observed by Peters and Bond, but the rest is really not filled. I will talk about this almost entire period in a second. Let me just show you somehow Ilka is involved into that. We are currently working on a paper where the phase shift between the cycle is varying every about 70 years. So this would be a full change here. So Ilka and I have actually contributed with data to this project because for such analysis it is desirable to go into the past as far as possible. There is one thing which is missing. So we are expecting, if this works like this, we are expecting a change in the phase leading at about the 1830s, but this hasn't been covered in the diagram you've seen before. Here you see there's practically nothing. In this you can't really do any statistics there. But, of course, the discoverer of the Schwabe cycle himself, Heinrich Schwabe, was observing all this time for 40-something years, 42 years. And these observations are still preserved in the library of the Royal Astronomical Society. And they will cover precisely this period. And I went there in August and took about 7,000 images of his observations, which is really incredibly a lot. And the accuracy is very, very nice, finely drawn. They're all very small, 5 centimeters in diameter, but they're very precisely drawn.
Photograph the books or what?
Yes, exactly. So they're all there in digital form, and I will try to analyze them as soon as I find time for a student. Yeah, that's about what I wanted to say. So this is future music. Thanks.
So cycle 0 is then the lost cycle?
No.
Is not one?
Cycle 0 is this one. Oh. Is this one. So this is 1, 2, 3, 4, and the lost would be 4 prime or so, would be this one, if there is any. But it looks like, so this also includes the Armand observations, that there is a small butterfly starting here. And statistically it seems to be sound, but it's very few points, of course.
Okay, but that's not actually the Staulacher data.
Both, they're combined, maybe 50-50, Staulacher and Armand.
It seems that this lost cycle is very big and very short,
Yes.
and that would contradict what Myers wrote. If it's weak, that must be long.
Right.
And from historical data set from tree rings and from isotopes, that this is very robust. The cycle is short and it's,
Right.
then it's high. So I think it's.
Well, although I mean, if you plot the cycle length, then cycle period, you have something like 10 years. Then you would have, if you don't include the lost cycle, you have something like this, and then you get this cycle and something else. And if you, well, but it should be long, of course.
Or maybe it's not the previous cycle.
Like this. And if you include this, then you get 2 shorter ones, like this. Maybe a bit asymmetric, like this. And it looks a bit more smooth than with just the long one. But of course,
This is also taking into account correlation with the height of the frames.
yeah.
The big cycle cannot be short.
What about beryllium data at the time?
I don't know. No beryllium data in Europe. Should be there.
No, but some data, 1,000 years historical data, and they show that this is,
1793, right?
there were cycles like 9 years,
Yes.
8 years, but they were very strong. So maybe we need some look more in archives,
Yeah, if you really could feel this period better, that would be.
And maybe we can look also for, for proxies, like, this rollers.
Yeah, they looked into that already.
Yeah.
There was some indication, but it's all
magnetic
indicated.
synthesis.
Yeah. But it's all just indicated. I mean, it's not really conclusive.
Readings, look at readings.
Yeah. Well, but the C14 has a very long delay, I think. Doesn't show the cycle.
I found some small note of myself that I was in London and in 41 volumes of Schwabe
Yes.
observations.
Yes,
correct?
exactly. This is what I went
And you
through.
photographed them all.
Yes. Except, I mean, there were drawings of the moon and stuff,
Yeah,
and
yeah.
Jupiter, I omitted them.
Yeah.
I have here the beryllium data. Can you find your cycle perhaps?
It would be 18. And the maximum is always the minimum here, right?
Should I put that in?
Yeah. Not yet. It's searching, maybe wait for a second. No, I think it went over analog artificial. Yeah. Okay. It's squeezed, but it doesn't matter really. So let's see. This would be 1800. This would be the last strong cycle, 85. And then we are saying 93, the new cycle should start. But there is a maximum here, which would say
Beryllium maximum means a
minimum.
solar minimum.
Yes. So that the only thing there is a little shoulder here, but it's not really saying anything. So the beryllium data would be against an additional cycle. So you have a relatively long distance between two minima, while the others are
Yes.
shorter.
Yes.
And that was interpreted as a lost cycle.
No. This would say there was no lost cycle, but just a long cycle.
Yes.
While the butterfly diagram might indicate that there's an additional cycle, a shorter one in between, a week shorter.
And there's cycle 4, or cycle 0.
This is cycle 4.
Uh-huh.
That's 5.
And what about your cycle 0? Is over there.
So
Or
4,
you would work.
3, 2, 1, 0. This were 1, 0 and 1. This would be the 2.
Alright. They're very close.
But 12. 4.
You can make
No, I
some
think
drawings
that one.
on the whiteboard if you.
I think there are none.
I think that one. You're just pointing.
Yeah, but then there's too many. I think the beryllium data is not 100% correlated.
Oh yeah, but the arrow bars as well.
It's 50.
You should add on certain arrow bars to this. And where is this graph from?
From your pair.
Yeah, this is ice cores, right, from Greenland.
Oh.
I think one cannot really find a one-to-one correlation to the cycles.
May I ask about north-south domination? You said that there is a certain trend of it. How reliable north-south domination is in those cycles 0 to cycle 4?
Looked into the well, there was if you take the average latitude, so say whether that was into the north or south somehow, then you can say something. This was in this paper which is currently under review. I don't know the precise. there's a figure here now. No, really, it's. I don't have a figure of that.
So in your previous figure, you said that the cycle continues to grand minima and Dalton minima.
I don't know. I mean, if you look at the cycle period, this is
So
what
what is the period
If you
of
would-
cycle?
So it went down to something like 8 and 7 years or so for these two. Or if you don't believe in the lost cycle, then this would be something like 14.5 years or so.
Period 14.5
Yeah,
years.
14 or 15 years, I don't remember.
Almost like the present one.
There's some
It's very long. If you measure it from minimum, from previous minimum to minimum, it's very long. 50 years.
13.
From minimum to minimum. From maximum, you measure it maybe 7 years.
Yeah.
And Will was actually saying that the current maximum may already be lost one.
Yes.
Already coming.
Looks like 13 years or so.
Right. Right.
Okay, let's then run again.
To the cafeteria down there.
What time are we going to? 2 o'clock or 3:30. And then we have a break between 3:30 and 4 and 4 o'clock. Yes, it's right. The new system on my computer. Fingers crossed. No.
I was thinking maybe you could save some time by
It works for us, but we have a problem
Well,
with memory.
the thing is,
We're short on memory, and
in the
now
beginning we were however, when we started doing our
no, after he transferred random around.
it's really the signature of Azimuth is very, very different.
Is it yours?
Radio and reading, so it's quite, one has to band
After I
a lot of things in order to explain.
they transferred, the situation became worse. So I have to.
This from
Yeah. It's Windows, yes.
No, it's a failure of the program.
Essentially, you don't believe it.
Of what?
Of the coder.
I don't
who
remember.
programmed it.
You must have ordered that from
Your race structure is going to be explained by using kochukhov+pelt+arlt and doing
Yeah. I mean, Harvard gets always the
same thing as you were showing.